This question is the example from Hansen and Singleton's 1982 paper. And this is one of the first paper that uses the GMM to estimate an economics model. Right. I explained it briefly in the class, and basically nothing special. We are interested in dynamic optimization of consumption, and we assume CRRA assumption, utility function, and then we have to have the Euler equation, right? So today's marginal utility must equal to tomorrow's marginal utility. And Z is all the available information at the time of the decision, right? When you decide how much to consume, Z will be included. Usually, like say, you may include, say, the previous year's uh, interest rate, right? T minus 1. Or you may also use the previous year's consumption or the previous year's uh, growth rate, something like that. And also, if you are, if you have, like, you may use like wage rate, wage, or like a lot of things. Okay. So details, but if you are interested in the details, ask your macroeconomics professor. Anyhow, so by the way, so this is a conditional expectation form. Something given zt equals to 1 or like, so if you, it is conditional expectation, and in econometrics, conditional expectation is very difficult to handle because it must be satisfied for each value of z, right? So usually an easier way to handle this information is to change it into uh, like unconditional expectation, right? So this is what I suggest, okay? So instead of having conditional on z, I have z times something equals to 0. So it is conditional mean independence assumption, but this is uncorrelated in its assumption. So other than that, it's pretty obvious. So then let's think about moment function. What is the moment function? We are going to use, so because the moment we are using is ct plus 1 over ct times minus gamma minus 1 equals to 0. This is the moment we are utilizing for our estimation. So by the way, let me simplify this guy as say B. Okay, B is the consumption growth, right? So I will write this as ZT times beta RT times BT minus gamma minus 1 equals 0. So I will define G now, will GT beta and gamma is ZT times beta RT BT minus gamma minus 1. That's it. Yeah. This is the moment function. Of course, beta and gamma are unobserved and everything else is observed. Z is observed, our interest rate, B is the consumption growth rate, all observed. Okay. Now from now on, it is simple algebra. So let's calculate omega. That is gt theta. By the way, I'm going to write it as theta. Theta is beta and gamma. Theta 0 and gt theta 0 transpose is the variance of your moment, and nothing much we can do here actually. It is just beta 0 times rt times bt minus gamma minus 1 squared, gamma 0, times zt times zt transpose. That's all. We cannot simplify any further than this, right? So if you make more assumptions, you may simplify the form a little more, but from our economics model, in our consumption optimization model, there is no more natural assumptions we may utilize. So I'm going to leave as it is, right? And C, let's differentiate. Um, let's differentiate the moment function. So let me just do it one by one. So I'm going to differentiate with respect to beta first, which is easy, right? It is simply zt times rt bt minus gamma. Okay, so beta is here, so you are going to differentiate with respect to that. And if you differentiate the moment function with respect to gamma, then you are going to differentiate with respect to this guy. So you are going to get minus gamma times zt times beta times rt times bt minus gamma minus 1. That is this is the derivative with respect to gamma. So then as a whole, right, the total derivative is, so you have to write it as excuse me, put it this way, gt with respect to beta, comma, gt with respect to gamma side by side. So that means if zt is m dimension, then it is m by 1, it is m by 1. Because theta is two-dimensional, so it should be m by 2 dimensions. So there are 2 columns. That means you may just copy what we did. So zt rt bt minus gamma, the first guy, minus gamma times zt beta rt bt minus gamma minus 1. Or if you want to factor them out, you may put it this way. Say zt is together rt bt minus gamma are coming together, and we are going to multiply 1 and minus gamma times bt minus 1. Beta. Beta again. So this is another form, but it does not help to simplify what we do. Okay, then let's think about T. How can we construct the optimal weighting matrix? The optimal weighting matrix is omega inverse, but omega was very weird. It was beta rt bt minus gamma minus 1 square times zt transpose. Okay, we have to utilize this form. So first, as usual, the expect population mean will be replaced by the sample mean, and and then the next problem is unknown parameters, beta and gamma. Beta and gamma are the main problems we have to handle. So you have to use two-stage GMM, right? My suggestion here is your theta tilde n is arg minimum, say theta, for g hat n theta transpose g hat n theta, where g hat n is defined as 1 over n summation gt, t here, of course, gt theta. So what I'm doing here is the weighting matrix is set as identity matrix. The weighting matrix is simplified, kind of an arbitrary weight, but it doesn't need to be identity, but that would be maybe the simplest weight. So then I'm going to estimate omega hat as sample mean of same thing. So beta tilde n, which is part of theta tilde, times rt bt minus gamma tilde n minus 1 squared. So you can calculate everything. Beta tilde is obtained here, calculated here. Gamma tilde is also calculated here. RT, BT are data, what you observe. So also ZT transpose are observed data. Okay, so this is computable. You can calculate every part of this, and then let W hat inverse as excuse me, let W hat n be omega hat inverse. Okay, so calculate this first and then invert it to obtain the weight. Okay, so this is how you calculate the weight. Actually, there is nothing special. It's just a little more annoying algebra. Now then, let's calculate the variance. Variance is pretty easy. Variance is, we know the formula, G transpose omega inverse times G inverse, right? So we are just doing it carefully, but actually there is nothing to be simplified, right? So remember, GT was this, by the way, I didn't define that. G was expectation of this, that's just expectation of this guy, okay? So it is expectation of, right, ZT RT times BT minus gamma 0 times 1 and beta BT minus 1, beta 0. Minus gamma, excuse me. Minus gamma 0, beta 0. So this is all. Right? So there is nothing we can do. And also, omega is given like this. There is nothing to be simplified, right? So, I'm really sorry, but that's all. Like, we cannot do. There is nothing further we can do. Just I don't expect you to do the algebra. Algebra is just useless. Now then, let's think about how to calculate the variance. So the variance will be G hat transpose times omega hat n inverse times G hat n and total inverse, right? So you just calculate each of them. They are easy. Let's think about omega hat n. By the way, so here, let me change the notation here. I'm going to write it as omega tilde. Omega tilde uses gamma tilde and beta tilde. They are from the preliminary first step estimation, okay? But now, when you calculate the variance, you may use t equals 1, and you may use just the final estimator, beta hat, instead of beta tilde. Beta hat RT BT minus gamma hat n minus 1 squared ZT transpose. This is the difference. Again, the only difference here is the estimator you are using here is different from the optimal weighting matrix. And G is also pretty simple. It is, again, 1 over n sigma, and just copy this. Let's see, I'm not sure if I can remember it correctly. BT, RT, BT minus gamma hat n, and 1 and minus gamma hat n, beta hat n, BT minus 1. So you can calculate everything here. And then plug them in each of them. Then you will get the variance estimator. Okay, good.